All right, so that makes sense, but what happens to the electrons in the conductor if I'm not applying a potential? Do they just stay put and do absolutely nothing?
Oh, that's a great question. No, they don't. So at anything but absolute 0 Kelvin, right, if there's any sort of heat, if there's any temperature, like a room temperature, they're actually constantly wiggling around. They're just shooting back and forth, boom, 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 boom. But if there's no potential, it's random in all directions. So there's no net drift of the electrons in any particular direction. They're just sort of zipping around, randomly smacking into stuff and just doing this. When you apply an electric field or an electric potential V, then not only do you have this thermal motion, but you're biasing it so you get a drift in a particular direction down the wire. That's current flowing down the wire. And what's neat about this is that we'll come back to this much later, but it's this randomness, that contributes in part to what people call noise, right? That there's this little bit of signal that's always there that you can't quite ever get to 0.
Because the electrons are always moving.
They're always doing something, unless, of course, you're at absolute Kelvin.
All right, so that totally makes sense, but I still get this feeling that something's not quite right? If I'm an electron and I'd like to go, say for example, we're here in California and I want to call my friend in Texas.
Okay.
I can pick up my cell phone and do that nearly instantaneously. And a good part of that is due to the electrons moving in my phone or in different, in the phone.
Okay,
line.
so why is this bugging you? I'm not sure where you're going with it.
Well, if electrons are constantly trying to start and then stopping and ramming into the atoms of the conductor, how can my signal, which has to be carried by electrons, get all the way to Texas?
Oh, you're saying if there's a wire between here and Texas, how could information transfer, at the speed of light between here and Texas if the electrons are doing all this crazy stuff? Okay, but so think about it this way. Think about a tube filled with marbles all in a row. The tube is only as wide as a single marble. It's as long, this is an old analogy, a long tube of marbles. And so one end is in Texas and one end is here in California.
It's a
It's a long pipe of marble. So I take another marble and I push it into the end, right? So what happens at the speed of light? A marble pops out in Texas.
Almost instantaneously.
Almost instantaneously. But I didn't, my actual marble, the one that I put in the input, didn't travel all the way to Texas. So that's the way to think about it. These things are always kind of zipping along with some drift velocity, right? But when you're transferring information, it's sort of the interaction that gets transferred all the way across the wire.
So Michelle, does that mean that resistors are only good for throttling current? I mean, that sounds useful, but can they do anything else really other than generate heat?
Well, I mean, resistors always follow the expression V equals IR. It just turns out that we can put that to lots of uses. So some of them are going to be setting conditions within a circuit. So we'll do all sorts of interesting things. As we move down, we'll learn about biasing transistors and things. But one of the easier ones is, in fact, that R can change as a function of all sorts of environmental variables, right? So temperature, pressure, light, all sorts of things can change the R value of a particular object. And so they end up being pretty good sensors. You can have all sorts of resistive-based sensors.
I see. So the sorts of sensors that we might want to put on a robot at some point.
Exactly. So let's look at a couple of them, because I think one of them we're going to end up putting on a robot.